Now the continuation. Yes. For the brute force, we know, although it is pretty easy to use the brute force method to solve a computing problem, but most likely your solution using the brute force will be a bad solution. Likely, yeah, likely, especially when you have a non-trivial solution, a non-trivial problem. All right, yeah. For example, if we just look at our polynomial evaluation problem, many people could treat it as a trivial problem, very easy, but actually it's non-trivial. Right? We know if we use Horner's rule, we can reduce the number of multiplications significantly. How big we can reduce the number of multiplications? Yeah. So let me, prepare the writing here. Yeah. All right. Yeah. Now we learn the asymptotic notation. Yeah. So we know before we apply the Horner's rule, we just use the brute force method. Yeah. The one before we use the Horner's rule, that's the brute force method. That's the one we're talking about here. All right. So what is the growth function order? Yeah, I can ask you in many ways. What is the efficiency? Asymptotic notation of the efficiency. To write it more precisely, I can use the big theta notation, n squared, right? Big theta of n squared. Remember 1/2, we add up all the multiplications. That is 1/2 times n times parenthesis n minus 1. We just take the leading term, 1/2 n minus squared, leading term. Drop the 1/2 or replace it by 1 as the leading coefficient, we get n squared. That is its that is the growth function. Growth function n squared. All right. Yeah. So that's the brute force method. After we apply the Horner's rule, we improve it. We get a big theta of just the n. That's the improvement. Big theta of n. That's the improvement. Very big improvement. So on paper, you see, from 2 to 1, that improvement, right? That 2 to 1. Yeah. But actually, remember, I use one simple example. When n equals how big? 1 million, right? I remember I used the 1 million. When n equals 1 million, the ratio to method 1, the Horner's rule uses 1 second, the other one 5.8 days. That's the huge difference. So here you can see difference is 2 and 1 difference. But from that example, 5.8 days and 1 second. Yeah. All right. So that is our old experience, old background. All right. Now we start our new content. Still, the problem is solved. Problem number 5, we did sort n array. We did. Remember, selection sort. All right. But here we revisited. In this class, I counted approximately we need to learn 6 sorting algorithms. At least 6. At least 6 sorting algorithms. So this is number 2. But this one, we learned it before. Actually, it's an old one. But here we use a new concept to understand. Still, some interesting properties we can learn. Given an array, how to solve it in ascending order. Yeah, you're familiar with it. Why we need to solve it another time before we go to the solution? Some students may argue we already have a solution, selection sort. Yeah. Selection sort, the efficiency is this one, big theta of n squared. We have it. Why we need to do it another time, right? It looks like redundant. You already have a solution. If you cannot get a better solution, why you do it another time, right? Yeah. So that looks like a legitimate question, but here I have another argument. Pretty old. Sean, did you look at my new announcement this morning?
Yes, sorry, I was just finishing some work.
All right, yeah, okay, yeah. So, yeah, next time, yeah, I allow you first take something minutes, yeah, finish whatever you need to do. After that, yeah, so we just focus on the lectures, because this I got a lot of experience from this. I remember several years ago when I taught evening classes, my database class, half of the students watch the laptops in my class, half, 20-something students classroom, about one half students. Just do something in the laptops, whatever. Yeah, but first few times, so I feel it's okay. Yeah. So, but after I did a midterm test, I realized those students very poor. Those students, very hard to give succeeds. Those students. But those students who really pay attention in the past did much better. I did statistics. 20 points. 2 groups, 20 points. So after that, so then I just, I didn't put in my syllabus because I like to, give it in a graceful way. Not just, but in future, probably I will put in syllabus. Because the impact is huge. The impact is huge. So that's fine. All right. Okay. Yeah, let us continue. Why we need to solve it another time. All right. Yeah. So in this class, for some of the questions we solve many times. So we take this view. Yeah. Remember, we want to learn the problem solving. We want to, so the goal in this class, the main goal in this class, learning the problem solving skills, knowledge, techniques. That's the main goal. But in problem solving, your thinking is the most important. The thinking is the most important. Question. Oh, yeah. Oh, thank you. Yeah, Jude. All right. Enter another time. Yeah. Oh, yeah. Yeah. Thank you. Too. Yeah. All right. So. Right. Yeah. So the thinking methods. So here the thing is here I use this term. A problem is a carrier of a set of thinking methods that result in different solutions. Carrier. All right. A problem. Here we have a sorting problem. The sorting problem can hold multiple thinking methods, different thinking methods for us. All right. For example, we have 3 methods we can use to solve this problem. These 3 methods will be very useful in our real world problem solving. The next thing is, how do you memorize these 3 methods? The question is, after you learn these 3 methods, how can you memorize these 3 methods? Not easy, right? How can you memorize it? That's the 1 to 3. It's very hard. But when we have a carrier, we can memorize some much easier. The carrier is solved an array, sorting problem. This problem we know. Oh, solving this problem. There are 3 methods. We know how to use 3 methods to solve this problem. Then, next time when we try to solve a new problem in the real world, I don't have any idea to solve this problem. Okay. Oh, let me look at this problem looks similar to the sorting problem. Okay. So then we look at the solutions, all the solutions in the sorting problem, and see which one can be used in this situation. So that's the reason we use this understanding. Okay? Yeah. So the goal is not just to find a solution. The goal is we want to have more thinking methods in our mind, in our brain. All right, yeah. Next. The thinking methods are important, yeah. So definitely, yeah. So we emphasize that, yeah, because the students tend to emphasize the answers of the questions. They tend to emphasize that. What's that? So they only need to know the correct answers. Usually, the students have that kind of mentality. Just give me the correct answers. Okay? But I want to say the thinking methods are more important than answers. Thinking methods are more important than answers. The reason is simple. If you the answers of this question, you cannot use that answer to help you solve other questions, right? Just one answer, simple, right? But if you master all these methods, you can use them to solve many other problems. So that's why more important than the answer. All right, yeah. So here, let's look at a new solution. Okay. It's not redundant because the thinking is completely different. Well, how do you get a new thinking method? We need a view based on special property. A new method comes from a new property. The older one, we use the selection property, yeah, because there is order ranks for the elements in the array. We use that property to solve. Here we do not use that property. Here we try to find a new property to help us solve this problem. So what's that new property? Observation. What is that property? Let's look at the diagram. Look at the diagram. Help us understand the problem visually. Let us look at it. Here I select 2 elements in the array. Let us compare these 2 elements in the array and see what is the typical special property between these 2 elements. Suppose these 2 elements are out of order. What do you mean out of order? It's easy. In the order, in ascending order, that's the order we want to have, right? Yeah. Our goal, ascending order. Out of order, that means descending, right? X, A sub I plus 1 is less than A sub I. Out of order. Here we consider out of order case. Yeah. Critical property. Yeah. Here we make our critical observation if the array is not sorted. there must be two adjacent elements that are outerable. Is that probably true? Two adjacent elements outerable. Can you imagine that? If an array is not sorted. Yeah. So in problem solving, to discover this kind of problem, extremely important. We can call insight. You can call the insight of this problem. You get the insight. So that's the critical step in solving this problem. All right. So now, if someone points it out to you, then it's easy, right? But to discover it, it's hard. Discover it, it is hard. All right. Now, a reference. Here, I want to introduce a new concept called inversion concept. That out of order, we provided official name. Official name. Out of order, because we don't want to call it out of order all the time, right? We want to provide a formal official name to it. Definition: a pair of elements, A sub I, A sub j. This time we do not require two adjacent elements. Arbitrary locations in this array. I location, J location. More general. No restriction to adjacent. All right. It's called an inversion if when the subscript I less than subscript j, one, the subscript number less than the other, but the value for the element with smaller subscript is greater than the value of an element with larger subscript. That's the inversion. Because if it's sorted, we expect A sub I less than or equal to A sub j. But now it's not. Now not what we want. That means we have an inversion in this array. That is called a one inversion. If you find one pair of elements satisfying this condition, we call one inversion. Because in one array, you can find many inversions. Many inversions. Later, I will give you questions, ask you finding the inversions in a given array. Okay? Yeah. I hope after you understand this concept, just count it carefully. Inversion, number of inversions. All right. Yeah. Then we get to this problem. If the array is not sorted, think about it. And we use the inversion terminology to describe if the array is not sorted. There must be an inversion. How about that? Is that simple? If there is no inversion, it must be sorted. Right? Yeah. Think about that. But the other way, the array is not sorted. There must be at least one inversion, right? Yeah. Okay. Yes. All right. Then we want to move another step further. If the array is not sorted, there must be an adjacent inversion. How about that? An adjacent inversion. How about that? Is that true? Yeah. Think about that. Adjacent. Here, look at this critical problem. Does that mean an adjacent inversion? Right? An adjacent inversion out of order, but now we replace out of order by the inversion concept. Okay? Yeah. All right. Compare the difference between these two problems. Both correct. Both correct. But can you talk about the main difference here? Both correct, right? But there must be some difference that will impact the solution in our sorting method. Think about that. Anyone say something here? Inversion. Both inversions, but different types of inversions. The first one we call global inversion. Global, two elements distributed globally, spread globally. The second one we call adjacent local. Adjacent local. So typically we replace global inversion by local inversion. What is the impact of that? What is the impact between fixing a global inversion and fixing a local inversion? What's the difference? Fixing global is much harder, right? Fixing local inversion is it much easier? Because two are adjacent. Yeah. You just swap, quickly. For global, the problem is you need to do a lot of work. How do you locate a global inversion, right? You need to locate them first. Then you need to find a way to keep track of them, right? Maybe you get lost, right? Yeah. So for that reason, to solve this problem, we want to use the local inversion view as the critical property, as the insight to solve this problem, computing problem. That's the main point. All right, next, let's move to the solution details. All right. Yeah, right. I already talked about that. How to fix it? I already mentioned swap operation. Okay? Yeah, everybody knows how to do the swap operation. Very basic. Implementation idea. All right. How enough to implement in order to reduce the number of inversions? To solve it, basically we just want to reduce the number of inversions in the array. If we can reduce that number to 0, we solve it. How about that? We reduce, suppose we start from 100. So then every time we use swap operation to reduce the number of inversions. At the end, when we reduce that number to 0, we solve it. That's simple. Okay? That is a completely different view from our selection software, right? Yeah. But it's also variable, right? Yeah, useful. All right, let's look at the procedure. How do we do it? Step 1, start from the first element for each scan. Yeah, we need to scan our array multiple rounds. Yeah. In order to reduce or remove all the inversions, yeah, we start from the first element for each scan. Number 2, do swaps one by one from left to right. Do swap operation if necessary, right? If in order, then we do not do swap. Only when those two adjacent elements, remember, here we consider adjacent elements. Only when we find two adjacent elements form an inversion, we do the swap operation. Otherwise, pass those two elements. Next pair, every time, look at do comparison of two adjacent elements and do swap if necessary. All right, yeah. Okay, all right. Step 3, start at the first in-place element. In-place, you know the meaning of in-place, right? If an element is already in the correct location, we call in-place. All right. So what's the meaning? Because when you do scan, you have to stop somewhere, right? You have to stop somewhere. Yeah. Stop at the end, that's one way, but we don't want to do the redundant work. We want to reduce the redundant work. So how do we reduce? So here we reduce in this way. Suppose this is array, okay? The first scan, think about after the first scan. Is there any element in place already after the first scan? Can you see any element in place after the first scan? Swap. Okay. When you reach the end, look at it. How about the last element? The last element must be the maximum, right? Think about it. Because when we fix the inversion for each two adjacent elements, the largest element always move to the new location. How about that? Suppose when we start, the largest element is somewhere in the middle, okay? Let me put the max. Every time when you do one swap operation, the max element moves to the next one, right? Because there must be a swap. It is the largest. Then the next one, another swap. After you finish the whole scan, the maximum element must be at the end. How about that? If it is at the end, we call it in place, right? All right. Now, we need to do the second round scanning, second round. For second round, do we need to do redundant work with the max, last one? Already in place, why you do it? It is in place, don't touch it. It is already in place. If you touch it, redundant work. You're wasting your computation resource. Don't do it. We want to save our computation resource. So the second round, we stop right in front of the max element. In front of it, we stop. Okay? All right. But when we stop, do we put the second to last element here, second to last? So the third time we stop in front of those elements already in place, right? And so on. Every time we put at least one element in place, at least one element in place. And finally, the last round, we only compare two elements, the last one. Look at that. Completely new idea, new method, new thinking, right? It's good or not, we don't know. If it's good or not, we don't know. Yeah. Right. But it's interesting. Hey, it's a new solution. It's interesting. Yeah. All right. Yeah. So here, a summary. Yeah. There is one element in place for every scan, at least one. The in place element of each scan appears at the end of the current array. Yeah. Every time we work on the current array. The current array, we eliminate those elements already in place. Elimination method, eliminate elements already in place. Yeah. And the current array is a subarray that excludes all the in place elements. Right? Yeah. So size reduction. Here, size reduction. All right. Yeah. Current array, the size becomes smaller and smaller. All right. Then visual imagination. And the last common visual imagination. The swap looks like a bubble moving to the right, from left to the right. So that's why you know that the bubble swap. Here you can see, I spent a lot of time talking about bubble swap. You already learned bubble swap in CS 2250. For the reason I revisit that same solution, we introduce inversion concept, the new thinking method, that kind of thing. I think it didn't learn in CS 2250. I taught that course twice. I know in that course we just provide a solution. So we don't provide the thinking concept thinking, all the details. All right, that is our sorting method number 2. All right, we can do efficiency analysis here. Yeah. The number of swap operations and compare. When we do efficiency analysis, remember, we need to identify the basic operation, right? When we do the counting, we should count. Oh, sorry. I made a big mistake. I made a big mistake. I didn't hook up my microphone. Wow. You see, a lot of details. Anyway. Yeah. Next time I need to write checklist, on a piece of paper, checkbox one by one. All right, yeah. Efficiency analysis, the same as what we did in selection sort. So yeah, I don't want to repeat it. All right. All right, yeah, the basic operation. Yeah, I talked about basic operation because we have 2 operations we use in the bubble sort. One is the comparison, another is the swap operation. Based on your understanding, which one you pick, comparison or swap as the basic operation. Okay, good, perfect. Yeah, I'll swap. Although the swap operation is the obvious one we need to deal with, right? Yeah. The reason, can you explain the reason a little bit?
Swap is more complicated.
Yeah. All right, yeah. All right. So because comparison, when we get every pair of adjacent elements, we need to do comparison. So we may not need to do swap, right? The swap we only need to do when necessary. If it's not necessary, we don't do the swap. All right? Think about, is it possible for a given array there is no swap operation? Can you think about that? Is there a possibility? Yes. The array already sorted. No swap operation. Yeah. So that's why we say the basic operation is comparison, not swap operation. Yeah. Okay. All right, good. Yeah. Yeah. All right. Yeah. We answer this question. Next topic. Actually, the last topic is brute force. So we finished this module, module 2. Brute force. We solved one simple problem, string matching problem. Mathematical representation. In this one, I'd like to talk about mathematical representation. For a computing problem, it is important. Our problem number 6, string matching. Given a string of n characters, we call that string text. And a string of n characters patterned with n less than or equal to n. Text and a pattern, n and n. Find a substring of the text that matches the pattern. That's simple. That's simple. You can see this problem is very useful in real world life, right? Real world. When you search a string in a text, we need this, right? Someone needs to write a program to do this. Think about how to write a program to do this, right? Here, we solve it. Because here we are talking about brute force method, brute force method. So typically shown laptop, the laptop. Yeah. All right. When we're talking about the brute force method, typically we should have two methods. One lower level brute force, another advanced, more sophisticated method. So here we also have, but that sophisticated one extremely complicated. Much faster, but extremely complicated. Also in our textbook. So probably I cannot talk about that in our class. That's so complicated. You will get lost. So complicated. If it's possible, I can talk about solution, record a video. So if you're interested, you just watch my video. Otherwise, you just pass it. So complicated. But you can see string matching, how can you solve it in a different way than brute force? Brute force we don't want to solve. Right? You just compare all the possibilities. That's the brute force. But then complex one, you do not have to compare all the possible substrates. You can scale many substrates. But how to scale? Very complex. How to determine, you keep track of, many special locations. And then do the math comparison. When this condition satisfies, you do comparison. If not, you will go to the next one. Some things like that. All right, so let's look at a simple solution first here. All right, find its location. Yeah. Where is the starting point of that set substring in the text? We need to find that starting location. All right. The index I of the leftmost character. That's our goal. All right. First solution, yeah, brute force. Brute force always our first solution. Okay. All right. We need to represent the problem in mathematical representation. Then we can apply math tools. Yeah, so this is very important. Otherwise, we have many advanced math tools, but we cannot apply. Okay? So we need to make good mathematical representation here. All right, here it's simple. The test, we use a sequence of symbols like that. P with subscripts. Location from 0 to n-1. Straightforward representation. Okay. And a pattern sequence, P sequence, subscripts from 0 to n-1. Okay. Straightforward. All right, so next. Then the requirement. What do we need to do? Requirement, we need to write it mathematically. Find the location I such that Ti, yeah, you find the right location. Starting from there, there is a match pattern. The pattern is matched, right? So here, how do we describe that pattern is matched? T sub I equals the first character in the pattern, P0. After that, T sub J, I plus J. Yeah, this J can be 1, 2, 3, 4. Right? I plus J equals PJ. Yeah, a little abstract. Yeah. Okay, try to connect. Okay, you move subscript of T one position to the right, you should also move the subscript of P one position to the right. Same pace, right? Same pace. That's the one by one character matching. Yep. Until you reach the last character in the pattern. Pattern, but not in the text. The text, you have much longer text. So you finish one substring comparison. Subscript comparison, just one. Okay? But you can do many after that. All right. Strategy here, because we need to look at the number of comparisons we need to solve this problem using the straightforward method, the brute force. How many comparisons? At this point, can you tell me the number of comparisons? It may not be easy, right? Yeah. So let us work on it. Here, I want to introduce another commonly used strategy. It is called guess and verify strategy. Guess and verify strategy. I think you know this strategy. Everyone knows this strategy. But here I emphasize this strategy, and you will see if you learn how to use it, you can solve many problems. Guess and verify. This guess step also very important. You need to make a good guess. You need to make a good guess. May not be exact guess. Yeah. May not be exact, but later you will see a good guess will lead to a solution quickly. Okay? Yeah, we try to understand the strategy using many examples. Let's start thinking. Question: can we exhaust all such n strings here? Because we are using the brute force method. Usually, another meaning for the brute force method, another important property of the brute force method, exhaust all possibilities. Another problem, or the problem. Exhaust all possibilities. But for advanced methods, we do not exhaust. For advanced methods, what's the typical way used for advanced method? We find the very important property. We find a very important one. With that property, we can eliminate large number of cases. Then we don't have to exhaust. We already eliminate large number of cases. We only need to work on relatively small number of cases. That's the advanced method. But brute force exhausts all the cases. All right. Every time extract an n string, n string, yeah, we call it the short way n string with n characters, consecutive characters in the string and substring from the text with consecutive characters. Okay, every time extract one, then do comparison, right? Compare it with the pattern for the possible match. That's it. Yeah. But the question is, how many such n strings? It's a counting question, right? Can you count the number of n string, possible n strings in a given text? Yeah, it's simple. It's a simple question, but here there is some method. There is some useful, important method I want to introduce here. Yeah. All right. Here, first, we apply the strategy. Make a guess. All right. The text has n characters. N characters. Substring n characters. Can we use n and n to represent how many, the answer, number of substrings? Anyone has an idea? Just make a guess. The guess, not necessarily correct, but we want to make as close as possible. Not necessarily the exact answer, but close to the answer. That's a good guess. Close to the answer. That's a good guess. Anyone wants to make a guess here? Make a good guess. Using n and n. Okay? N and n. In what arithmetic operation you will get your answer? What kind of arithmetic operation you will get? Just guess. Nothing to lose. Nothing to lose. Imagine the comparison. Make a guess. Okay. Let me see. All right. Yeah. Is it n minus n, or close? Because when you make a guess, we know it should be less than n, right? It cannot be n, right? Yeah. Because your n string occupies some space. Yeah. Yeah. You use that to measure. You use an n string, measure, go through your n text. Okay, n string, substring. Yeah. So this is a close guess, but we may not be exact. Okay, so that's why guess and verify. You need a verify step to tell us if this is correct or not. If it's not correct, we need to fix it. Okay, now we want to check if n and n is correct guess or not. How to check? Another strategy we used before in our first class. We already used that strategy. Start from simple. Simplest case, right? Simplest case. Yeah. What is the simplest n when n equals n? How about that? The text greater or equal to n. How about we consider n equals n? Same. The text only has n characters. Is that easy in that situation? Yeah. You can get an answer easily, right? Yeah. When n equals n, how many n substrings can you find in the text? N, yeah, n equals n. How many different n substrings? N different substrings. The whole string, I want to ask you the number of whole string, not the number of characters. You may tell me the number of characters. I want to ask you the number of n string you can, possibly you can find in the text. How many? One. Yeah.
But if you do n minus n, will be
0. Yeah, that's why this guess is wrong. That's my point. Yeah, because our guess we only need it close to the answer, not necessarily exact. Right? Nobody is so smart they can make a guess exact the answer, right? Yeah. So that's why we need to do the verification to fix the difference, the gap. Okay, fix the gap. Yeah. But when you plug in, this one gives you 0, but we know the answer is 1. That means we should adjust it, right? How do you adjust it? How do you adjust it to make it correct guess? +1, right? +1. Yeah, this one is 0. So our answer, after we make an adjustment, +1. N minus n +1. This method. Think about this method. This method. Okay. Fix it. They can guess. Fix it. Verify. Okay. All right. Now, implementation details. So we want to complete the solution quickly. All right. Yeah. We're ready. Yeah. Because we understand, we spend a lot of time. Now we're ready to get a solution. Look at the first and substrate. In this case, leftmost index subscript I equals 0. Now, we want to look at the last and subscript. Can anyone tell me the corresponding subscript for the leftmost character of the last and subscript? People need to calculate it, right? But here, I want to introduce a new method to calculate the correct calculation. The method is important. The problem is easy. The method is important. So let me introduce that method. Very powerful method. Looks simple, but extremely important. So what's that? How to figure out the subscript. A method to do it. Okay. Here, there is in math, there is important problem solving idea. If invariant idea. Try to find a quantity that is invariant when you move other factors. Here, we need to move our n subscripts along the line, right? From left to right, we need to move. When you move, many things change, but there is some special quantity never change. That is the invariant quantity. Invariant quantity. If you can find that, you get a problem solved. Invariant, identify. What is the invariant quantity? Difference of 2 n subscript of each subscript. For each subscript, if you take the difference of leftmost subscript, rightmost subscript, is that difference always the same when you move? Yep. The length is the same, right? The difference also is the same. Yeah. You never change the length, right? When you move. Okay? Subscript moving, the subscripts of each character keep moving, right? Yeah. But the difference never changes. That's the invariant. That's what we call the invariant. All right. All right. Based on that observation, that invariant, we can set up a simple equation. So what's that? Let's set up. For the first substrate, let's take the difference. What's that? Rightmost subscript n minus 1, leftmost minus 0. Here, rightmost n minus 1, leftmost, let's say x. Okay, unknown, x, okay? They must be the same, right? They must be. So then solving this equation for x, is that easy? Okay, x equals n minus n. Think about that. This method. Invariant idea, it's simple, but this method is important. Later, we will use this method to solve many other problems. Later, I will show you, using this method, we can solve many other problems. Okay. Yeah. All right, first time we use this method. All right. After that, now after we can figure out the location of the last n substring, can we do the counting easily? Can we do the counting easily from 0 through n minus n? Can we do the counting easily? Right? Yes. Okay. Yeah. So, all right. Yeah. Okay. Now we find the I for the last n subscript. Now, efficiency. Best case efficiency. When you do the string matching, the best case efficiency, you only do one substring comparison. You know, the first n substring, after you do character by character comparison, you're done. That's the best case. But the number of characters you need to do the comparison. One substring, but you need to compare all the characters. So that's why you need to do n character comparisons. Worst case, all the way to the end. All the way to the end. All right. The number of character comparisons for each n substring, but you have this many. Remember, this many. Our guess verification, right? This many. Okay. And we can prove here the last subscript, the first. We count the number of different subscripts. The same number here. We can also count them to get the answer. This is the worst case efficiency. How about the average case efficiency? We have the best case, we have the worst case. How about the average case efficiency? Okay. Adding up divided by 2. Because 1, 2, 3, 4, you know, it's the cases. You have 1 substring, 2 substring, 3, and so on. Right? So that's all the cases you have. So you can add them up, divided by a number, so you will get this one. Yeah. So the average case efficiency. All right. Any question? Yeah. So we finish our module 2. You can see several important idea methods we learned. Simple problems, but those methods important. Okay, done. All right. So let me finish this PowerPoint file, but I still have 10-something minutes. I can start the next PowerPoint slides. Next, module 3. Yeah, so let's start a little bit, then we take a break. Yeah, because we don't want to waste even 10 minutes. That's a lot for us. Okay, all right. The title, module 3, recursive algorithms. So this is a very important topic, module, recursive algorithms. Yeah. You learned before, yeah, but here we need to learn much deeper, in a much deeper way here. Yeah. Part A, introduction to recursive algorithms. 8.1, the first topic. First view of recursive algorithms. Yeah. So let me start it. All right. Why recursive thinking is important in problem solving? Let's look at some basic understanding, basic high-level understanding. Why recursive? You know how to do the recursion, yeah, I believe. Still from your CS2250. And actually, there is one problem you learn in CS2250 using the recursion. Very famous puzzle problem, another puzzle problem, famous. Power of Hanoi problem. Yeah. We will do that again here. Yeah. We'll do that again here. Yeah. Because some new view I want to talk about here. we're used to straightforward, that's non-recursive thinking in problem solving. Most people, they like to do straightforward thinking, non-recursive, because that would be, easier to understand. Yeah. But when you have more and more experience, you will get used to that recursive thinking. Some problems can be solved both non-recursively and recursively. Actually, maybe you can use both ways, recursively, non-recursively. So here we want to compare them, advantages and disadvantages between these two methods. Power of recursion. First, I want to talk about the power of recursion. It is very powerful, so why people use it? Because it is very powerful. The main reason recursion is so useful. It is powerful. It's powerful in problem solving, totally powerful in problem solving. More specifically, you can solve a very complicated problem. If you use recursion, the solution looks pretty easy. That's the power of recursion. Okay? If you use recursion, so easy, but if you do not use recursion, extremely powerful. That's the power of recursion. Okay? Some relatively hard problems can only, because there is some possible argument here, so I put in the parentheses, be solved by recursion. Some problems extremely hard if you do not use recursion. You cannot imagine how to solve it. There are many such problems. Anyway, yeah, that's the power. But here, let us compare, other than the power, we want to do comparison of other aspects. Iterative, yeah, if it's not recursive, we call it iterative. Iteration for loops using loops in a iterative way. Recursive way, recursive. Iterative way typically is less resource, but harder implementation. Resource-wise, recursively use more resource than iterative. Why? I can explain. More resource, but easier implementation. Why more resource? Here, I do not want to go too far, but here I just give you some quick answer. Why less resource? Why more resource? Yeah. Think about the recursion implementation in programming language. The programming language, they need to build a mechanism to support recursion, right? Because many early programming languages, they do not support. They do not support recursion. Then later, programming languages become more and more advanced, then they support recursion. Okay? Yeah, the internal implementation using a special data structure, stack data structure. Yeah, so let me change the color. All right, okay. Stack data structure. In the recursion implementation, how to do it? Using the stack. You push the recursive function call into the stack. Because the first time when you call recursion, you cannot get an answer. You need to do another recursion, so you need to do many recursions to get an answer, right? If you cannot get an answer, you push it into the stack. All right. So when you have many recursions, you push many recursions into that stack. All right. When you, at some point, you can get an answer at the top of the stack. Pop it. Okay. Then another one. You can use the known answer to get the next one. Pop it out. Okay. And then finally, you reach the bottom. You process the whole stack. You get a whole answer. That's the typical way to implement recursion. But the stack uses a lot of memory, right? Resource. And especially when the stack is very deep, with a large number of recursions, the stack is very deep, then you will get out of memory problem. Out of memory. Stack overflow, right? You heard of stack overflow? Yeah, so that's the problem. You get stack overflow. Because the memory is not big enough to hold your stack. Your stack is too big. The memory cannot hold it. Stack overflow. That's the typical problem. Okay, so that's the recursion problem. A lot of resource. All right. So that's the thing. Next, our problem number 7, calculate the factorial. A very simple question, but here we use the recursion point of view. Because when you calculate factorial, you just calculate directly. You just use a calculator or math software. But here, we want to treat it as a recursion problem and try to study some special properties. All right, let's take a break because when we start a new problem, I want to put in a second half. So we do not need to stop in the middle, so we can from beginning to end. So let's take a break, and still we come back at 2:30. We start our second half. All right, so the break time